This is an example of a kinematics problem. Poorly tuned car accelerates from rest to a speed of 28 meters per second in 20 seconds. So if I'm looking to solve this problem, the first problem asks me to just graph this situation. So we'll say, let's see, 20 seconds, so 5, 10, 15, 20. There will be 20 seconds. This will be 10 seconds. And it's a velocity versus time graph, so we need to go up to 28 meters per second. So 5, 10, 15, 20, 25, not going to be quite enough. We'll say 5, 10, 15, 20, 25, 30, right here, meters per second. Each one of these is 5, 28 at 20 seconds ends there, and we know it's constantly accelerating, which means there's a constant slope, and so therefore our velocity versus time graph looks more or less like that. Part A asks for a well-labeled diagram of the situation, so that would essentially look like a very poorly drawn car, which starts out at rest and ends after moving to the right. It ends going 28 meters per second, and that's its final velocity. The time involved is 20 seconds. Okay. We also have an initial position, and we have a final position. We don't know anything about them so far. Part C asks us to calculate the average acceleration of the car. Well, if we write down our kinematic inventory of our 6 variables, we know that the initial position, we can go ahead and call that 0 meters. We don't know where it ends up. My final velocity is positive 28 meters per second. My initial velocity is 0 meters per second. The acceleration is unknown. The time involved is 20 seconds. So if I'm looking to find the average acceleration, I know I cannot afford to have my final position. So I choose the appropriate kinematic equation that doesn't include position. That's going to be v equals v initial plus at. So therefore a equals v minus v initial over t. When I plug in my values, I get 28 minus 0 divided by 20. And so I get 28 over 20 meters per second squared, and I could plug that into my calculator and find out what the numerical answer for that is. How far does it travel in that time? Well, now that I know the acceleration, I can look for the final position. Or I could decide, I could do part D first and say, well, let me find an equation that doesn't include acceleration but does include position. Well, I'm going to take that track, and we're going to say final position equals initial position plus 1/2 v initial plus v final times t. That's another one of our kinematic equations. And if we're looking for how far does it travel, we're really looking for the difference between initial and final position, or its displacement. So the displacement just equals 1/2 v initial plus v final times t. So 1/2, v initial is 0, v final is 28, t is 20. And in this case, my displacement would be 1/2 times 28 times 20, which would be 280 meters. So once again, I chose an equation that involved the thing that I wanted to find, but did not involve